This is Coach Dorf. We're going to continue our discussion about calculus, and in particular, we're going to talk about the derivatives as rates of change in the sciences. Now, when we've talked about the meaning of the derivatives in the past, we've talked about three different ideas there. The derivative can be the slope of the tangent line, the derivative can be the rate of change, and the derivative can equal the velocity if my original function is position or height. And the second derivative is then the acceleration. Today, we're going to use some examples from science that highlight the second and third meaning here. And with this section, then, we have basically three common types of problems or examples that we'll see. The first type that we will see will be an example where an object is thrown in the air, and we need to find certain things related to that. That could be its velocity, its height, maximum height, its velocity when it hits the ground, accelerations, and so forth, those types of things. The second type will be ones which we are given an equation or a formula to describe a function, and that these are used in STEM. Now, when I say STEM, I mean science, technology, engineering, and mathematics. So the sciences there. And we'll be given that equation, and then we'll need to find some information related to it. Often these will be something related to the rate of change. And the third type that we'll see will be a particle moving according to some formula or equation. And again, in these, we will also then be finding things like maybe its velocity, acceleration, when it's speeding up, when it's slowing down, so forth, and those things. Now, in my lecture notes, I have examples of all of these. Also, the homework videos that I've made has examples of number 1 and number 3 in here. In this video, I'm going to do some more examples, and I'm going to focus on number 1 and number 2. So, but if you look at all of these resources, my lecture notes, this video, and the homework videos, you'll get examples of all of these to help you understand them better. So let's start with a first example here. And this is going to be an example of the type that we have for number 1. And here we have a ball is thrown in the air, so vertically upward, and suppose the height of the ball in meters after t seconds is given by the formula S of t equals 48t minus 16t squared. So this is going to be, this is like, just put like this here, this is like type 1 here, object is thrown into the air. And then we're asked to find some things. So let's see, part A will say find its velocity. All right, so what is its velocity? Well, we're given that S of t is 48t minus 16t squared. So its velocity, represented by v here, is the derivative of that function. And so that's going to be 48 minus 32t using the power rule here. And the units here are going to be meters per second. So have that there. Another thing that we could find is here is what is the maximum height of the ball. So maybe to draw a picture here, what's happening here is we're throwing this ball up and it goes up like this. And it has a parabola shape, and we know it's a parabola shape because we have, our formula has a t squared here. The fact that it's a negative in front of it, a negative number in front of that, means that it's an upside down parabola, so an upside down U, like this. All right. Maximum height is going to happen here. That's the max height. And if you wanted to think about this in terms of units here, we would have something like this. This axis represents time, and this axis represents height. So what is the maximum height of that ball given that formula there? Well, the maximum height is going to happen, that happens when velocity is 0. Because you're throwing the ball up, it goes up, and it's let me do this in green here. You're going up, the velocity is increasing. At the very top of it, the velocity stops there. Let me do that again. Goes there. Velocity is 0. It's a positive velocity as it's going up, and then when it comes down, it's a negative velocity, and at the very top of it, the velocity is 0. So we'll use that fact then. So remember, the velocity from what we did in part A was 48 minus 32t. If we set that equal to 0, we can now solve for t, and that will give us the time that we're at the top. Now, that doesn't give us the maximum height, but we need to figure out the time first in order to figure out the maximum height. So this problem really has two parts to it. All right, so we've got this. So I bring the 32 onto the other side. I get 48 equals 32t. Divide by 32, and I get t equals 48 over 32, which then if I divide by the top and bottom by 16, I get 3/2, and that's seconds. So that's when, so at 3/2 seconds, the ball has velocity equal to 0 and is at its maximum height. So what is that height? Well, we now take that time t and we plug that back into the formula that we got for its height, which is s of t. So we use s of t equal 48t minus 16t squared, and we use t equals 3/2 seconds. So s of 3/2, put that in there. I'm going to get 48 times 3/2 minus 16 times 3/2 squared. All right, and I can work this out either by myself, or I can use a calculator or Desmos on the computer to do this. And I will see I'll get 72 minus 36, which is 36, and that's meters. And that's how high up it is. So this height here, where it's at its maximum, the time is 3/2 seconds, and the height there gives me a value of 36 meters. Good. Now let's do another one. What is its velocity when the height is 32 feet or 32 meters on the way up? Now you may wonder, why do we have this on the way up here? Well, if I throw my ball up like this, and again, we think of this in terms of an axis here, here's time, and here's height, meters. We know at the very top it's 36 meters, and 32 is going to be below that. Well, there's going to be a time up here where it's going up and has a height of 32 meters. And there's another time here where it's going down. So this is going up, this is going down, where it also has a height of 32 meters. So we're interested in this first one here. Again, like the previous problem, involves a couple steps. I need to first figure out when is the time that happens. And then once I find the time, then I can put that into the velocity and figure out what the velocity is. All right, so first find the time when the height equals 32 meters on the way up. All right, so I'm going to take my original equation. Remember, that was s of t is 48t minus 16t squared. And I'm going to set it equal to 32. All right, to solve that, I'm going to bring everything over to one side. So I'm going to bring the 48t and the minus 16t squared over to the right side, and so that I get a positive number in front of the t squared. So 16t minus 48t plus 32 equals 0. So just again, make sure we're on the same side. I'm going to bring these things over here, but I'm going to write it on the left side when I get done. So when I do that, I get a plus 16t squared minus a 48t, and I'm adding that to the 32 to get the equation I have here. Now, how do I factor this? Well, I see that they both have everything has a 16 in common. So I take out a 16 and I end up with this. And then I can factor what's inside the parentheses to be t minus 2 and t minus 1 equals 0. Multiplying those two parentheses together, they equal 0. So when I multiply them together, so that means either one of those parentheses has to equal 0. So either I have either t minus 2 equals 0 or t minus 1 equals 0. And that means t equals 2 seconds or t equals 1 second. Now, why do I have two answers here? I would want to have one answer. Well, t equals 1 is the answer that we're looking for, because that's what it is at going up. The t equals 2 is what happens when it's going down. So if I go over to my graph here, I'm going to draw this in green. That height here happens at t equals 1, and this height here happens at t equals 2. And if you wanted to, just remember that when it reaches its max here, So max height was at 3/2 seconds. Notice that there's a symmetry here. That the 1 and the 2, halfway in between them is the 3/2. That will always happen when I have a parabolic formula. Parabolic means that I've got like t squared or an x squared in it. And that's my formula is a quadratic like that. So I'm not done. I found the time, but we're supposed to find the velocity. So we now need to find the velocity at t equals 1 second. So I remember from before that velocity, which was the derivative of s of t, is 48 minus 32 t. So we use that at t equals 1. And when we do that, we get v of 1 equals 48 minus 32 times 1, which is going to give me 16. And velocity is measured in meters per second. So that's what I get, 16 meters per second. If I were to do this, let's see, right. If I were to do this in terms of the way down, what I'm going to end up with is a negative number, and it's going to be negative 16 meters per second. Now, that may not be clear to you right here, but that's what it's going to happen. There's going to be a symmetry there that also works. So what have we done? We found its velocity in part A, then we found the maximum height of the ball, and then we found its velocity when the height is a certain height. In this case, it was 32. The last one I want to do is find the velocity when the ball hits the ground. All right, so again, this one, like parts B and C, there's multiple parts to this. So we have to first figure out what time it hits the ball, and then we can plug that into its velocity formula to figure out the velocity. All right, so when does the ball hit the ground? Well, that's going to hit the ground when the height is 0. So the ball hits the ground when s of t equals 0. And so my s of t, again, was 48t minus 16t squared. So we're going to set that equal to 0. And now I'm going to solve for that. To solve for that, look at this, and I'm going to factor out on the right that everything has a 16 in it and has a t. And in fact, I'm going to factor out a negative 16. So I'm going to factor out a negative 16t. When I do that from here, I'm going to get a t. And then when I factor that from this 48t, I'm going to get minus 3. So that's all going to equal 0. And so again, like we've had before, I've got these two parentheses, t and t minus 3 equaling 0. So either t equals 0 or t equals 3. And these are seconds. Why do I have two answers? Well, at t equals, this is a little confusing, I'll write seconds in here. At t equals 0, this is when the ball is initially thrown up, all right? Because the height is 0. When you got the ball and you initially throw it up, that's at t equals 0. And this here is when the ball hits the ground. So if I were to draw my graph again here, showing this, it's going to look something like this, maybe a little bit, make it a little bit smoother. And this again is time. Here is, write this in red, this is time. This is 3, this is 0. And remember, halfway in between was at the max, and that was here at 3/2. And we had here that the max happened at 36 meters. So this was height. And here is the height of 0. So what do I need to do? I'm trying to find, again, the velocity when the ball hits the ground. We determined that it hits the ground at 3 seconds. So now I'm just going to calculate the velocity at 3 seconds. And remember my velocity formula. I should write that in here. Velocity of t was 48 minus 32t. So velocity at 3 seconds is going to be 48 minus 32 times 3, which would be 48 minus 96, which is going to equal a negative 48, and that's going to be meters per second. Note here, the negative here means going or traveling down. And earlier we had an example where the velocity, this was positive v means going up. And that's what we had up here in that one. So there's one example of a problem of one of these word type problems here. Let's look at another example, and this example is going to be like common type 2. Way back at the beginning, so if we go back at the beginning here, we said that the first type of example was an object is thrown in the air. We just did that. Now we're going to do one where you're given an equation or a formula used in STEM, and you have to find something about that. So that's what we're going to do here. So this is going to be like number 2, right in purple, like we had there. So this one we have, so you've got the volume of a sphere is equal to 4/3 pi r cubed, where r is the radius. And you're supposed to find the rate of change. And I'll put this is instantaneous. Sometimes they'll put the word instantaneous in there, sometimes they won't. If they don't put it in there, then you would just assume you can assume that it's instantaneous. If they do put it in there, it just means rate of change. Find the rate of change with respect to its radius, which is r, when r equals 2. So what this looks like is I have a sphere, draw a sphere, so a 3-dimensional circle. Here's my radius, and the volume is 4/3 pi r cubed. All right, so we'll go back to black now for our solution. So you're supposed to find the rate of change. That's the derivative. So I'm given my formula v equals 4/3 pi r cubed. I'm supposed to find the derivative of that with respect to the radius. So I write that as dv dr. The v tells me what the formula I'm using. The r tells me what my variable is. So when I take this, I've got the 4/3 pi r cubed. I use the power rule, so I bring that 3 out front. So I have 4/3 pi 3r squared. And when I combine those, then the 3's will cancel out, and I get 4 pi r squared. Now, so that's the answer. That's the answer for the rate of change in general. And when r is 2, then we get that the rate of change equals 4 pi 2 squared, and 2 squared is 4. 4 times 4 is 16, so you get 16 pi. Now, just an interesting note, recall earlier when we did this example where we had a circle of radius r, the area was pi r squared, and if I took dA dr, you get, by the power rule, 2 pi r, which was the circumference. So the derivative of the area equals the circumference of it, or the perimeter, if you want to think of it that way. When I have a sphere, we have in this example of radius r, its volume is 4/3 pi r cubed, and the derivative of the volume with respect to r equals 4 pi r squared, and that equals the surface area of the ball. Where the volume is, if you were to fill it with water, that would be its volume. The surface area would be, if you painted the outside of it, that's the surface area. So there's a symmetry here. What happens for this circle in 2 dimensions also happens for the sphere in 3 dimensions. I think that's really cool that those things happen. And in general, they don't happen in math. If I were to take a different shape than a circle, if I took a square, it doesn't work if I take half of its length to be my variable. All right, just I think a cool type of problem. Let me do another example of this type. And what I mean by this type, this is going to be, again, like we said, type 2 from above, where type 2 is this. Now I'll use a different color here. This is type 2. You're given an equation or a formula used in STEM. So that's the type 2 that we're going to be talking about here, just like we did it in this previous one. So in this example, we're going to do, so suppose f is given by this formula, 4a squared b cubed over c. And I want to do several parts. So I want you to first find the f, the a. So what this means is this f tells me the function or the formula, and a tells me the variable that I have here. So I'm going to be, in this problem, I'm going to be taking f equals 4a squared over b cubed times b cubed over c. I'm going to be taking the derivative of the right-hand side, where a is my variable and everything else acts like a constant. And so I'm going to put this a little bit here, maybe do this in purple again. Everything else acts like a constant. So because I'm doing the f, my a is my variable for this problem. So I'm going to write has f equals a squared. I'm going to pull the a out with this exponent and then just put everything else in this parentheses here. So again, this is going to be a variable and this part x like a constant. So then df dA, I'm just going to take the derivative of a squared, what I have circled in red, and that's 2a, and I don't do anything to what's circled in the green because that's going to act like a constant. Now I'm just going to rewrite that so it looks more like what we started with. So I put the numbers out front. So I've got 2 times 4, that's 8. Then I put the a on top, and I've got times b cubed, and then in the denominator I c. And that's my answer for df dA. We can do this for lots of different variables. So we could find df dB, all right? So same idea, but now b is my variable. So I'm going to write f as, so f originally was 2a squared. Sorry, that's not right. It was originally 4a squared b cubed over c. So I'm going to write that, bring the b out front and put everything else here. And this is going to act as constant, and this is my variable. All right, so then when I do figure out df dB, I take my derivative of b cubed, which would be 3b squared, and then I keep what's in green there inside the parentheses as a constant. Don't change it. And then to make it look more like what I started with, multiply the 3 times the 4, I get 12. And then I have a squared b squared in the numerator all over c. And that's my answer. All right, and you can figure out we have one left to do. That's a df dc, where now c is my variable. I'll do the same thing in writing f, which was 4a squared b cubed over c. I'm going to bring the c out front, and I'm going to get 4a squared b cubed inside there. This x as the constant, and this is my variable. And I'm going to rewrite this one more step. I'm going to write c with an exponent, so that's going to be c to the negative 1. 1 over c is the same as c to the negative 1. And now when I take the f dc, I get, by the derivative, I'm taking derivative of c, so it's negative 1 c to the negative 2. By the power rule, I bring the exponent out front, so that's why I get negative 1. And then I put c to the power, I subtract 1 from 1, so negative 1 minus 1 gives me a negative 2. And then what's in the parentheses doesn't change because that acts like a constant. And then I can rewrite this as negative 1 over c squared times 4a squared b cubed, or I can write that as negative 4a squared b cubed all over c squared. And that's my answer there. One last example here. Again, this is going to be of 2 here. And this one is a cool problem. And you'll probably notice that this is a problem that's a homework one that you have. So I'm going to do this one because I think it's such a cool problem, and it's a hard one, I think, for you to figure out all of it. So this problem says that you have a violin, and the frequency of the vibration of a vibrating violin string is given by a formula. And that formula is f equals 1 over 2L times the square root of t over this rho, which looks like a p, but it's actually a Greek letter called rho. All right. And so what do these things mean? F is the frequency of vibration of the violin string, and L equals the length of the string. Let me change my little tab on my pen here. Equals the length of the string. B equals the tension of the string, and rho equals the linear density of the string. And now if I were to, let me see if I can draw a violin here, make sense here in real life. So here we're going to do part A. We're going to say we're going to find the rate of change of the frequency, so that's f, with respect to L. Okay? And then we'll do part 2. Still trying to find a pen cover that works. Find the rate of change, there we go, of f with respect to rho. So we got those two parts here. So we've got this formula, And this formula is F equals 1 over 2L square root of T over rho, or P. I don't think of it that way. This is very similar to the previous example. So for part one, we have L equals our variable. Everything else on the right side acts like a constant. So I'm going to rewrite F. F was 1 over 2L square root of T rho. L is my variable, so I'm going to put that out front. I get 1 over L, and then I got 1/2 square root of T over rho. So this is my variable. This part, it's like a constant. Okay, and I'm going to rewrite this so that it's 1 over L is like L to the -1. And when I take the derivative, then df dl, then I'm going to get -1 L to the -2 times what's inside the parentheses. And then I can write that as -1 over L squared, 1/2 times the square root of T over rho, like that. Now I could clean that up a little bit if you really wanted to. It doesn't make a big difference. Put the 2 out front, which is probably the way they would have it in the back of the book. So df dl equals that. Again, the fact that we have an L here means that that's my variable, and that's what we did with this problem. Now in part 2 of this, it says we're going to now let this rho or P be the variable, and we're finding then df d rho there. That's the rate of change with respect to rho. Let me make sure that that's clear here. In this first one, the rate of change of F with respect to L is df dl. And that's what we found here with this one. In this next one, we're finding the rate of change of F with respect to rho. That is this here, df d rho. So we're finding the rate of change of F, the frequency, with respect to linear density, or that's a P or rho there. So then to do this one, all right, we've got my function F, which is 1 over 2L square root of T over rho. I want to get the rho out because this is going to be this is my variable. So I want to put it in a way so it's easier to take its derivative. So I could rewrite as 1 over 2L square root of T over square root of rho. And now I want to bring the rho out front. So that's 1 over square root of rho, and put everything else inside this parentheses. So I get that. And so just make sure that's clear. Here's my variable, and everything else here, this acts like a constant. And now it'd be easier to write this 1 over square root of rho as that's 1 over rho to the 1/2 power times what's inside the parentheses. That's not changing. And then I could write that as rho to the -1/2 times this, what's inside the parentheses. I like this better because now it's easier to take the power rule. Again, this is my variable, and this here acts like a constant. So when I do df d rho, I do the power rule. I get -1/2 rho, and then I go 1/2 minus 1, and then I keep what's in the parentheses the same, right? And so then df d rho is -1/2 rho to the -3/2, 1 over 2L over T. And so I could write that as -1 over 2 rho to the 3/2, and then write down my parentheses like this. That's a perfectly fine answer. Some people would, including maybe the back of the book, would write this as 2 rho square root of rho times 1 over 2L square root of T. So there's different ways that this can be written. They're going to turn out to be the same. I could also write this as, maybe it would help doing it this way, to get a -1 over 2L. Let me go step back for a second here. All right. So I'm going to have a negative square root of T in the numerator. And then I could have a 4L to this P to the 3/2 power. This is probably the nice way to write that. So, but this way is okay, and this way is okay also. I've seen those answers like that. So that's just doing the calculus here. Now let's do another part to this problem here. That was part A. Part B is says that the pitch of a note that's played by the violin increases, is the same thing or is equal to the frequency of the note increasing. Likewise, the pitch going down is equivalent to the frequency going down. So if the frequency goes down, the pitch goes down. If the frequency goes up, the pitch goes up, and so forth. All right, and the questions are, when the length of a string is decreased, what happens to the pitch? Now, what does this mean in real life? So if you're playing a violin, you put your finger on the board there, so somewhere in between the string, you've decreased the length of the string. What happens to the note or to the pitch of the note there? Well, it's going to go up. Let's see how this works using the calculus that we've done here. So again, recall from part A. So from part A, number 1, we found, let's go back there, we've got this. So the change, the FDL is equal to -1 over 2L squared. Let's go back a little bit here. 2L squared times square root of T over rho. I think that's what we have there. That's what we found in part A. So what do we notice about this? So notice the FDL is negative. Why is it negative? Because we have a negative sign there, and everything else is positive. Everything else has to be positive, so that gives us negative. So notice that that's negative there. All right, so what does that mean? So because it's negative, if I look at the graph of it, now let me draw that in black here. I draw the graph of it, and this is my length here, and this is my frequency. It's going to be going down somehow because it's negative. The derivative is negative, so the slope of the tangent lines are negative, so the graph is going down like that. And so if the length of the string is decreasing, that means, I'll draw this in purple, so the length is decreasing. That means we're going farther to the left. We're getting closer to 0. That means that L is getting smaller and closer to 0. What happens F on the graph? Well, draw this in green. I have a point on the graph here. It's as L gets smaller, it's getting larger. So F is increasing. All right. So what happens here? So as the length is getting smaller, F is increasing, so the frequency is increasing. But what did we were told at the beginning? We were told that the pitch increases as the frequency increases. Since the pitch increases equals F increasing, we have the pitch of the note is increasing. So what is this saying in layman's terms? That means if you have your violin and you put your finger on the note, you're decreasing the length of the string. And as you're decreasing the length of the string, then the pitch is getting higher or increasing. So you get a higher note. That's really cool, I think, that there's all this calculus and science behind what's happening while you're playing the violin. All right, let's do another example here. In part A, we also calculated this rho, this linear density. So we're going to now ask then, when the linear density rho is increased, what happens to the pitch? Now, linear density, I think of the linear density as like the thickness of the string. So I play the cello, which is like a violin. If you look at the strings on those instruments, they don't all have the same thickness. The thicker the string is, the lower the pitch. So if I'm increasing the linear density, that means my thickness of the string is increasing. What should happen to the pitch? It should get lower. So the lower notes that are played by a string are the ones with an increased density. How does that relate then with what we've got here in calculus, where we've got this? So again, from part A, this time number 2, we had the F d rho. So it's a change of the frequency with respect to the linear density was given. Let's see, where did we find that? That was right here. We use this one. I'm circling in blue. So that was negative square root of T over 4L rho to the 3/2 power. So what is happening in this case with this function here? So again, I've got a function where df dt is negative. So we're going to just notice here, notice df d rho is negative. Why is it negative? Because we have this negative sign here and everything else is positive. So it's negative. So my function again is decreasing. Now though, I have, this is my rho, my linear density, and this here is my frequency. And the question asks if the linear density is increasing. So that means I'm going to the right on my graph, going this way. So linear density is increasing, going to the right. What happens to the frequency? Well, the frequency is on my graph here. So as I go, as rho is increasing, I'm going farther to the right. Oops, my frequency is decreasing. So this means that this results in the frequency is decreasing. So what do I have here then? So we've got that the df rho is negative. I look at my graph. So by the graph of f with respect to rho, f is decreasing. So as rho increases, f decreases. And since the pitch decreases equals the frequency increasing, we have pitch decreases, which is just what we thought would happen, right? If I have a thicker string, then the pitch is lower on there. Now, some of you, just to make sure we all understand this here, let me get this here. How do I get rid of this? Oops, I didn't want that. How do I get this graph? Again, so let me go over that. Here's my pitch, my linear density. Here's my frequency. We know that df d rho is less than 0. So it's a decreasing function. So as I go from left to right, the function has to get lower. So it's a decreasing function. If let's suppose I have df dt, we'll just say if df dt is positive, so I have this here, that means then it's increasing like this. All right, I think this is long enough. Again, use the videos that I've already created, the homework videos and the notes and these videos to help you with the homework. I didn't get a chance to do the third type of examples, but I have a really extensive homework video that explains how to do all those components, and it's in the lecture notes. All right, that should help you. Hope you have a great day. Thanks.